And it's recording. All right, hey guys. This is the first day that I'm gone. There's gonna be 2 videos because there's gonna be 2 class periods that I'm missing. Hope you're doing all right. Hope you don't miss me too much. We're gonna dive straight in to lesson 9.1. Okay. The gist of this unit is area, and perimeter, and then the of this lesson is area and perimeter, and then we'll look at specifically area and perimeter of circles in the next 2 lessons. We just ended a unit on circles and angles and circles and stuff like that, so we're still sticking on the circle theme. Okay. But okay, let's just dive straight into it. We're going to remind ourselves, what is area? Area is the space inside a figure. So we got a few quick, easy figures here that we're going to take a look at. We've got a rectangle. A rectangle's area is length times width, which hopefully we all know that. 9 times 3 is 27 inches squared. We use inches for length, inches squared for area, inches cubed for volume. Perimeter means to add up all the sides. Well, if we know that the bottom side is 9 inches, well then that top side is 9 inches. If the right side is 3 inches, then we know the left side is 3 inches because opposite sides are congruent. Just go ahead and add those up real quick. So perimeter here would be 9 plus 9 plus 3 plus 3, which is what? 18 plus 6 is 24 inches. Let's try to stay on top of our units, okay? Inches squared or centimeters squared or whatever for area, and then just plain old inches, centimeters, feet for perimeter. Hopefully you remember the area of a triangle is 1/2 base times height. If you don't, well, there you go. So in this situation, we have 1/2. The base is 7, and the height is 6. So 7 times 6 is 42. Divided by 2 is 21. And there's no units here, so we'll go units squared since it didn't tell us. We'll just speak plain. Excuse me. We'll just speak plainly with units. Perimeter means to add up all the sides, but guess what's a bit of a struggle here is we don't know how long this side is. How about I call it L? Okay, we don't know how long that side is, but we know, hopefully, we're kind of making a little bit of an assumption. It could have been better labeled for you here, that these 2 sides are the same. This is an isosceles triangle, so the 2 sides are the same. But how do we figure that out? Well, we've got a smaller right triangle, 2 small right triangles inside of that. So hopefully you can beat me to what I'm about to say. It's the Pythagorean Theorem. So a squared plus b squared equals c squared. But how long are each of these sides? If the whole thing is 7, well then each are 3.5 long. Yeah, each are 3.5 long. So 6 squared plus 3.5 squared equals L squared. I'm going to need to break out a calculator on this one, so I'll break out my phone here. That's 3.5 times 3.5 is 12.25. So plus 36. So that's, these add up to be 48.25. And then take the square root. I'm going to round. I got 6.946. How about I call it 6.95? Okay. So then if I want to know the perimeter, I'm just going to add up all 3 sides. We know that the bottom is 7, and then now we just discovered that each of these are 6.95 long. So add up all 3 sides. 6.95 plus 6.95 plus 7. We'll call it 20.9 units. Okay? This one here, this one's kind of, I like this problem. It's like a bunch of blocks that are shaded in, and each of them are 1 by 1. So each of them have an area of 1, right? If a square is, or this box, the area of a box is length times width. Well, each of the boxes is 1 by 1, so 1 times 1 is 1. So each of these has an area of 1, so just count them all up, right? How many are there? I don't really need to mark all of those as 1, do I? Hopefully you just know that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. So the area is 50 units squared, because again, I don't have an actual unit. And then perimeter, just add up all of the edges, right? The perimeter is the edges all added up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38. 38 units. Parallelogram, believe it or not, is the same thing as basically like a rectangle, base times height or length times width. But we call it base times height because the base here is 15, and then we're not taking the 14. Okay, that's not the height of the parallelogram, right? It's at a slant. The height is the measurement that goes straight up. So we're referring to the 11. So 15 times 11, I don't trust myself to do that in my head, 165 millimeters squared. And then the perimeter means to add up all of the edges, just as we have been. So if this one's 15, then that one's 15. If that one's 14, then, well, that one's 14. So 15 plus 15 plus 14 plus 14 is 58 millimeters. Okay, so that might have felt a little extra, right? Hopefully we're pretty comfortable with area and perimeter. That's a pretty fundamental thing. And but now where these figures had like an obvious like way to calculate them, right? Like I think we for the most part all know that like a rectangle is length times width. And we know that a triangle is 1/2 base times height. I feel like there's probably a pretty good chance that you know those things. And that's great. Those are really easy to calculate, and there will be problems that are that easy. But what about the moments where the figure like isn't perfectly something, right? Like take a look at this example 1 down here. I mean, it's a four-sided shape, but it's not like anything specific. I mean, the points are just randomly placed. How do we calculate the area of that? We kind of need a strategy to go about doing that. So let's kind of talk about that strategy here with these blanks. So we know that perimeter, recall that perimeter is the sum of the lengths of all the sides of a polygon. So that's what we were just doing there, right? Adding up all the sides. That's perimeter. And recall that area of a rectangle, that's what we just reminded ourselves of, is length times width. And that the area of a triangle is 1/2 base times height. We just used both of those things. So how can we all of a sudden use those fundamental things to calculate the area and perimeter of, say, this shape right here? This triangle, right? It's a triangle, and you might be saying, well, isn't that 1/2 base times height? Yeah, but how long is the base? What is the height, right? Like, I mean, I can draw in the height, but like, I don't know how long that is. I don't know what the height is. So we don't know enough about the triangle specifically, but what we do know is because of the way these coordinates are placed on the coordinate plane, we can see some right triangles being formed around our shape. Actually, let me use a different color. Right, there's 3 different right triangles that surround our triangle that we care about, okay? So when it comes to area, I know it doesn't, it says, the question right there says, how does the Pythagorean theorem help us find the perimeter and area, okay? So let's address the area first. When it comes to area, we can take the box, right? Look at, there's a box that surrounds the triangle, and we can subtract away the right triangles around it because we know the base and height of those. That's easy, right? I can clearly see that this is like 1 wide and 1, 2, 3, 4 tall. So the base is 1 and the height is 4. Those measurements are not clear about the black triangle, but they are clear about my colorful triangles that I've drawn in, okay? So we know the area of a box, that's length times width. Subtract away the stuff we don't care about, and we're going to be left with the triangle that we do care about. And then when it comes to perimeter, look at this. This is the hypotenuse, I'm going to call it C over and over and over, of each of those right triangles. A squared plus B squared equals C squared. A squared plus B squared equals C squared. A squared plus B squared equals C squared. We can calculate the hypotenuse of all 3 and then just add them all up. So perimeter is add up all those hypotenuses. Hypotenuses? Is that even a word? Can we plural hypotenuses? The hypotenuse? Whatever. And we can use the Pythagorean theorem to find each of those. I just want to take a minute right now in the middle of the lesson to tell you that if you've never watched the stream before, this is the stream. This is the setup. This is how I operate. But it's live, and you can ask me questions. So like right now, if you have a question about something that I've written down, it's kind of hard for you to ask right now, right? Because this is a recording. But imagine this experience live, and there's a chat, and you can literally type something to me, right? It's anonymous. You can just ask away, right? It's this experience, except not only are you just watching, you can ask a question. So if you feel like you're getting something from this and that you appreciate this, I'd suggest that you maybe check out the stream. That's not a promotion for me. It's something to help you out, right? All right, enough about that. So let's do it all the way through on one problem here, this quadrilateral. So clearly, let me draw a box and say brown. There is a box that, let me get it thicker. There is a box, that's too thick. Sorry. There we go. There is a box that surrounds this entire figure. Okay. And what are the dimensions of that box? It is 1, 2, 3, 4, 5, 6, 7, 8, 9 wide, and 1, 2, 3, 4, 5, 6, 7, 8 tall. So the area of the box is 9 by 8, which is 72. Okay? But clearly that's not the area of the black quadrilateral that's inside of the box. Okay? There's 3 triangles that we need to get rid of, so to speak. Okay, we need to subtract them away. All right. Let me not do green twice. Let me do yellow. We need to subtract these. Yellow is probably going to be hard to see on the screen. Let me just do blue. So we need to subtract away the orange, green, and blue triangle, okay, to find the approximate area. So let's take care of business here. So let's write all the dimensions here. This orange triangle is 1, 2, 3, 4, 5, 6 wide. 1, 2, 3, 4, 5, 6 tall. Okay, 6 by, is that 1, 2, 3, 4, 5, 6? 1, 2, 3, 4, 5. Yep, 6 by 6. And then the green triangle is 2 tall and 1, 2, 3, 4, 5, 6, 7 wide. And the blue triangle is 2 wide and 1, 2, 3, 4, 5, 6, 7. Well, the entire 8 that I already have written there, so I'll write over it in blue. So let's find the area of each of these triangles. The orange one is 1/2 6 by 6, which is 18. And the green triangle is 1/2. Why am I doing 1/2? Because the triangle is 1/2 base times height. Okay. So 1/2 2 times 7, which is 7. And then the blue triangle is 1/2 2 times 8, which is 8. So the area of the orange triangle, 1/2 base times height, 36 divided by 2 is 18. The green triangle ends up being 7, and the blue triangle ends up being 8. So if we take these pieces, right? Let me just do it in black here in the end. If we take those triangles and subtract them away, it leaves us with, well, let me not. Do I have all my dimensions right? Yeah, okay. So it leaves us with 72 minus 18 minus 7 minus 8 is 39. We don't have any units, so we'll call it units squared. And then the perimeter. Ooh, the perimeter, I will be perfectly honest, is not the most fun thing in the world, because what do we have to do? The Pythagorean Theorem 3 times over. So we have A and B for each of these triangles. We have 6 and 6, that's A and B, we need to find C. We have 2 and 7, that's A and B, we need to find C. We have 2 and 8, that's A and B, we need to find C. So A squared plus B squared equals C squared 3 times over. So let's do it. So 6 squared plus 6 squared equals C squared. That's going to be 72 equals C squared. Take the square root. Square root of 72 is 8.5, we'll call it. And then the green triangle is 2 squared plus 7 squared equals C squared. 49 plus 4 is 53. And then take the square root. You end up with the square root of 53 is 7.3. And then the blue triangle, A squared plus B squared equals C squared. So that's 4 plus 64, that's 68. Take the square root. The square root of 68 is 8.2, we'll call it. All right, let me kind of zoom into this for you. Maybe you can, might have gone too quick. I'll give you a second to write those down before I keep going. I went to Cafe Rio, got the horchata. Okay. So, clarify that 8.5 is this measurement right here, that 7.3 is right there, and that 8.2 is right there. So that's not all of the sides of the figure, because the top side, where's my brown, is 3 up there. So when we add the figure, we've got 3 at the top plus my blue, which is 8.2, plus my green across the bottom, which is 7.3, and my diagonal 8.5 that is orange, getting me all the way back up to where I started. Those 4 edges added together comes out to a clean, because of the way we rounded, 27. There's only one example of this in the notes, because as you can tell, it's a little tedious, but I genuinely hope that you didn't look at this and go, oh, that was complicated, right? It's just piecing it together, right? There's all these little things that we know how to do, and we're just using those things to make the figure, right? Hopefully you can clearly see a box. Well, I don't need 3 of those pieces. I don't need any of those triangles. I care about what's left after the triangle. So subtract away each of those triangles, and the leftover area is the area of the figure. Well, each of these triangles leads me to the diagonals that are the edges of this figure, this quadrilateral, so I can use the Pythagorean Theorem 3 times over to get each of those diagonals. Something that we've done over and over and over. It's just that once you have all 3, you're going to add them all together, and that top side, because, well, that's perimeter, all of the edges added together. And to be perfectly honest, that's the way it's done. Like, I mean, there's no, when points can just be randomly placed anywhere on a coordinate plane, you wouldn't want a formula. You want a strategy to get you there, because there is no formulas for this. I mean, honestly, this random figure, right? There's nothing standard about it. Those points were just randomly placed on the coordinate plane, and boom, find the area. I could have moved them anywhere. There's no formula. It's just a strategy. So let's think about that when it comes to maybe some slight application problems. Here is a dog run or a dog pin, right? If you were to make a fence for your dog in your backyard or something like that, we can start to calculate the dimensions and the cost, as you'll see here in a second. So building a dog run in the backyard can be modeled by plotting the vertices. So -2, 2, there's B, and 0, 5, up 1, 2, 3, 4, 5, there's O, and 4, 1, 2, 3, 4, up 3, there's N, and then over 4, down 1, 2, 3, 4, there's E, and then S, -4, 1, 2, 3, 4, and down 1, 2, 3, 4, there's S. Isn't that clever, Bones? Oh my gosh, so clever. Okay, so Bones is the name of our pin. Let's connect these guys together. I hope you're very impressed by what I just did there, making those straight lines. Thank you. Okay, so there's our dog pin, our dog run, Bones. So fencing costs $16.85 per foot. What is the cost of the fencing for the dog run? So we just calculated area and perimeter like 4 times over. Once for this, difficult shape, or 5 times over, and 4 other times up here for pretty standard shapes. So we're definitely still dealing with area and perimeter, but I would ask of you to think about this for a second before I spoil the answer. What measurement is relevant for fencing? If I'm calculating fencing, something that surrounds my dog pen, the dog run, do I care about the perimeter or do I care about the area? Hopefully you're thinking the perimeter, right? Fencing that literally is a perimeter, right? You know, when you hear that saying like in the movies, like, oh, scan the perimeter, something like that, right? Oh, perimeter clear, right? They went around the edges, which is the fence, okay? So this fencing, we need to know the perimeter. How many feet around is this dog pen? Because for every foot, we're gonna pay $16.85 per foot. So let's get to it. What do we already clearly know? We clearly know that the bottom here is 1, 2, 3, 4, 5, 6, 7, 8 wide. And we know that this side here is 1, 2, 3, 4, 5, 6, 7 tall. So what I don't know and what I need to figure out are each of these diagonals. So I want to use the same strategy as I did before and draw a box around our figure, okay? Whoops. A little bit nicer. Okay, so there's our box, right? I mean, the 8 and the 7 are already helping me make a box, so I'm not going to draw it over them, okay? I'm just going to leave it as is. So there's our box, and you might see this. Well, let's break this up into some shapes. What shapes do you see here? There's this weird gap over here, right? And you might be thinking that and thinking that's weird too. Well, let's just break it up into, okay, here's a triangle, and here's a triangle. And honestly, that's just a rectangle right there. And let me draw that a little bit nicer. That's just a rectangle right there. And then let's do not lime green, let's do dark green over here. Okay? So what's going to help me figure out each of these diagonals? Well, the purple triangle here is definitely going to help me figure out the perimeter there. So what are the dimensions of that? That's 2 by 1, 2, 3, 4, 5, 6 tall. So 2 squared plus 6 squared equals c squared. 36 plus 4 is 40. And the square root of 40 is... What is the square root of 40? 6.3. So that's 6.3 long right there. And then there's this small red triangle. So let's figure out what's going on there. That's 2 by 1, 2, 3. So 2 squared plus 3 squared equals c squared. So 4 plus 9 is 13. And the square root of 13 is 3.6. Now, I hope I haven't lost you what I'm doing here, right? You can't just casually count this, right? What are you going to count this diagonal? There's no 1, 2. There's nothing to count, right? I can count straight up and I can count straight across, but I can't count straight diagonally. That doesn't make any sense, okay? So I have to arrive at this measurement through the Pythagorean Theorem. A squared 2, b squared 3 squared equals c squared, the thing we're trying to figure out. And I got 3.6. And then the last triangle, the green one in the top right, 1, 2, 3, 4 long, 2 tall, so 2 squared plus 4 squared equals c squared. That's 4 plus 16, so that's 20. And then take the square root. That is 4.5. So that's all that we need to know in order to figure out the perimeter. We now know that the perimeter is, well, I'll use the colors here. We've got the red piece, that's 3.6 feet long, plus the green piece, that's 4.5 feet long, plus the 7 down the side, plus the 8 across the bottom, plus the 6.3 back up. All in all, you get an answer of 3.6 plus 4.5 plus 7 plus 8 plus 6.3. 29.4 feet, right? Because this dog run said per foot here. And sorry, I was looking for where it said foot. An example A, or the question A here, blah, 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 per foot. We're dealing with feet. So if there's 29.4 feet of fencing, we're going to pay $16.85 for every foot. So multiply those two together. This dog fencing is going to cost us $495.39. Yep. Let's see this next question here. You decide to cover the ground with a rubber mat because it is easier to clean. If the matting costs $3.75 per square foot, how much will it cost to cover the ground of the dog run? So if we're covering the inside of the dog run, that's area, because that's, well, the inside part. Perimeter was the edges, the fencing. This rubber mat that we're putting in the bottom is the area. So let's calculate the area of the figure. Well, just like the strategy above, should we use the space? Yeah, let's use the space down here, and I'll just keep pinching in and out. That hopefully is okay with you watching in class. So let's calculate the area of the box, right? I'm using the exact same strategy up here. Take the box that surrounds the whole thing and subtract all the stuff we don't care about, and what we're left with is what we do care about. Okay? So the box is 8 by how big is it? 8 across the bottom, but the 7 was not the entire height now, was it? This was 7, but then there's 2 more here. So this is 9 by 8. Okay, I wrote 8 twice, but just stressing that the box that we drew here with all these shapes inside of it is 9 by 8. So the box has an area of 72 square feet. But we don't care about the purple triangle, the blue box, the red triangle, or the green triangle. We don't care about any of that stuff. So let's subtract it away. The area of the blue box, the box is, we've already got everything labeled. If you labeled everything with me, if not, take a minute here as I stare at it to label that it's 2 by 3. So the area of that box is 6. Then there's the purple triangle right below it. It's 2 by 6, as you can see right there. So 1/2 base times height for a triangle. Don't forget the 1/2. One half, 2 times 6 equals 6 as well. And then the red triangle, as you can see there, is 2 by 3, if you've already got it labeled. If not, label it now. It's 2 by 3. What's it look like? I'm going to try to draw it similar. Oh, I drew the purple triangle upside down. I was trying to make it look like the shape on the, like that. And then the red triangle also looks like that, but it's a little boxier. And I just said it's 2 by 3. So 1/2 2 by 3, that comes out to be 3. And then the green triangle is 4 by 2. So the green triangle is 4 by 2. 1/2 4 by 2. That's an area of 4. So we have the area of all 4 things that we don't care about. So if we take the box and subtract away all this stuff that we don't care about, we're going to be left with what we do care about, which is 72 minus 6 minus 6 minus 3 minus 4, 53 square feet. So, if every square foot is 375, take that 53. Let me write that a little nicer. Take that 53 and multiply it by $3.75, and the total cost is $198.75. I'll give you a moment there. So the strategies, let me just look at this. I'll scroll right back down here in a second. So look at the strategies that we used here. Look at the strategy that we used here. It's all the same, right? There are, okay, now you can hopefully see every number there. I'll pinch in just a little bit more. There you go. The strategies are the same. There's things that we know how to find the area of really easily. Right triangles and boxes. We can do that in our sleep. Length times width and 1/2 base times height. Boom, 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 boom. But it's these abnormal shapes that are a struggle. And, well, I shouldn't say they're a struggle. I should just say that there's no clean way to figure it out. There's just this strategy of, okay, turn this into things that we do know, right? I know how to find the area of these triangles and boxes. So if I've got this big box, subtract away the gunk, right? If I've got these right triangles, I can find all of the diagonals using the Pythagorean Theorem. So there's no clean cut way for abnormal shapes. It's just this strategy that hopefully, after seeing it a couple times, it makes sense, right? I hope. I personally don't see how it wouldn't. So, density, the density of an object is defined as, blanking the equation for density? DMV. Density equals mass divided by volume. And that's like in a three-dimensional sense. Right, the density of an object, right? Like, things that come to mind is think of like a styrofoam ball, a softball, a baseball, and like a skee ball, right? When you play skee ball or skee ball, are those heavy? Or think of like a shot put ball. Some of you in track and field. So a styrofoam ball, right? They're all like relatively the same size, right? A softball is a little bit bigger than a baseball, and maybe a shot put's a little bit bigger than a baseball too. But for just imagine that they're all basically the same size, right? They all have the same volume. They all have the same volume. Volume meaning how big they are, right? I can all hold them in basically the palm of my hand, right? They're all relatively the same size sphere. But the weight or the mass of each of the objects is different. A styrofoam ball is practically air. A softball, whatever it's made out of compared to a baseball, is just a little bit lighter, hence the name softball. And then a shot put ball, right, why people struggle to throw them very far and it takes a certain technique is because it's got a lot more mass to it. So they're all the same volume, but they all have a different mass. And density is the combination of those things. Mass divided by volume. Okay? But when it comes to something in a two-dimensional sense, right, this coordinate plane, and we're looking at a shape, right, we're going to talk about population density. So each state has its own area, right? Which I would consider the size. So where softballs and baseballs are all the same size, right? When I'm talking about the size of a state, I'm talking about its area. Okay? Some states much larger than others. For example, Rhode Island is very teeny. California literally takes up the entire side of the country. So their area is a lot different. But how about two states that are comparable? How about like Nevada and Utah, right? They're relatively probably the same size area. I don't know off the top of my head if they are, but look at them on a map. They're not like too crazy different. Okay, so let's just pretend they're the exact same area. Or even better yet, how about let me get the equation down. So population density is people. So density, that's population. So population density is equal to people per area of the state. So where density of the reason why I'm explaining this is because I think this is like kind of like an important concept. Density is something that definitely trickles over in your chemistry and physics classes as you take those type of science classes. And whether you believe it or not, some of you in this room are going to do something science-based. You're going to go to college and you're going to be in a science class. I don't know if you want to be a nurse. I don't know if you want to be a doctor. I don't know what you want to be, but there's a pretty high likelihood that a lot of you are going to be taking science classes, whether you believe it or not right now. And density is one of those things that's pretty relevant. So where density of an object is like how much crap can you cram in that object to make it like, and that's what makes it more dense, right? Where a softball and a baseball are practically the same size, I've shoved more crap into a baseball than I have a softball, which is why the baseball is heavier. Or the styrofoam versus the shot put ball. The styrofoam ball, there's practically nothing in it. It's just air. Whereas the shot put ball, that thing weighs a crap ton in comparison to a styrofoam ball, yet they're the same size because I shoved so much crap into it. So when we're talking about population density, if we have two states that are the exact same size, clearly, hopefully you realize this, that some states have more people in it than others. So if we shove more people into the same size shape, it's the same size state, we've made it more populous. We've made it more dense with people, hence the population density. So where Nevada, right, is like a freaking desert and there's like nobody here, and then you go to some, state over on the East Coast or something, right, where there's people all throughout it, right, that state is much more dense in comparison to us. We've got literally just open dead desert with nobody there. That's not very dense at all. That's like this styrofoam ball. There's nothing inside of it except for air. There's nothing out there except for deserts. There's no people. Okay? So I probably over-explained that a little bit too much, but I just want you to understand what it is that we're finding here. So, Vermont has a population of 621,760 people. Its border can be modeled by the trapezoid with vertices. Here's 0, 0, 0, 160. What are these? 2, 4, 6, 8. These are 20 apiece, it appears, right? 120, 140, 160, 180, 200. So 160, 24 right here. 160. And then 80, 160 is right here. And then 40, 0 is right there. So here is Vermont. So there's Vermont in all its glory. What are the dimensions of Vermont here? This is 160 tall 80 across. We don't know that diagonal. We're going to need to figure that out. So if I were to draw my box, it practically is a box except for this piece right here. So this is an additional 40, and this is also 160 tall. So now we can start to figure that D is sort of combining with my 40. Let me rewrite that. So plot the points, draw the trapezoid, check, find the area of the trapezoid. So this is practically a box, except we need to subtract that one triangle. Should I do that in a different color other than black? Yeah, let me do that. Let's do it in this lovely pink. But I'll still do the dimensions in black. 40 by 160. Okay. So find the area. Well, the area of the box is 80 by 160, right? Hopefully you can, I'm not going to draw over what I've already drawn, but B to C is 80 across the top, and B to A is 160 down the side. So there's our big old box. It's 80 by 160, which I don't know what that is. $12,800. And then our one singular triangle is 40 by, oops, can't forget the 1/2, 40 by 60. 1/2 base times height. 3,200. So if we subtract these two things, the result is the area is 9,600 square feet. Are we in meat? We're not. Are we in meat? Are we in feet? We're probably in miles. Yeah. Each one represents 1 mile. Feet would be, yeah, I don't know what I was thinking, right? That'd be a very teeny tiny state. Miles squared. Find the population density. So, what is the population? It gave it to you, 621,760 feet, divided by the area, which we just found to be 9,600. So, plug that into a calculator. What do we get at 621,760 divided by 9,600? 64.8 people per mile squared. So we'll round it to 65. So for every square mile, there's about 65 people, right? So, I mean, you imagine, like, you know, Vermont, it's, you know, East Coast filled with, you know, suburbs and some slight major cities. But, you know, as you're traveling around, you know, some random neighborhood, you just cut out a mile by mile block. And there's approximately 65 people inside of that block, right? One street is a mile long, another street up, you've just captured a block, right? Everybody inside that block, there's probably about 65 people. That's what that's saying. There's 65 people per 1 square mile. How about the state of Nevada? Let's plot our points. So 0, 250 at A, and 0, 450 is B, and 320, 450. These are each 10. So 10, 20. There's 320. C, 320, 0, all the way down here. And then that's it. I mean, that's what Nevada looks like. That's pretty accurate. So let's draw our lovely state. Oh, I thought it was gonna. You see what I went for there? I thought it was gonna like clean up all my lines. Let's draw this a little bit thicker. Let's give Nevada some thick lines here. Boom. And then boom. And then boom. And then boom. Why is that slanted? Can you tell me why that's slanted? I don't know, but I don't care. So, our dimensions here, let's do them in lovely orange for the... Ooh, what about these colors? Ooh, how about this one? Okay, so what are the dimensions? This is 320 across, right, from 0 to 320. And then all the way down is 450. Can you see that very well? Probably not. I just need to not use yellow, right? I should stop. We'll figure out that slant in a second. Well, really, we just need to know. We just need to make our box, right? I mean, we just care about the area, right? I'm thinking perimeter here. We don't care about the perimeter. We just care about the box. So here's our box right here, right? The dimensions of the box are 320 by 450. Check, we did it. But what we need to know are the dimensions of this triangle down here, so that way we can find the area of it. So it's 320 by 250 tall. So our box, that is the whole thing, is 450 by 320. And then we're going to, well, let's find that first before I get ahead of myself. 450 by 320, that's, jeez, 144,000 square miles. Yikes. And then our triangle here, I guess I'll draw in some colors. Our triangle here is 1/2 250. That's a nice blue. By 320. Very pastel-y. 0.5 times 250 times 320. 40,000. So when you do that subtraction, it comes out to be, let's get black. Oh, comes out to be 104,000 square miles. And population density is people 2,723,322 divided by 104,000. So 2,723,322 divided by 104,000 is approximately 26 people per mile squared. So Nevada, I'm going to end this at the 55-minute mark. Nevada is 26 people per mile squared, while Vermont is 65 people per mile squared. So again, density is relative to the space. So there's less people in Vermont, yet more dense. That's because even though there's less people, they're cramming them in a smaller space. Nevada's huge. So even though it has a lot of people, there's space for those people. So our density is tinier. But Vermont, which has less people, those less people are fitting in a tinier space. So as a result, it's more dense. Okay. So this video just got showed to you by the sub that's in the room. Thank you. I appreciate you. Students, just so you know, everybody, this will be posted on Canvas. You can rewatch it again. You can fast forward to a part that you didn't get, something like that. It'll be there for you. There is still a homework on Canvas. There will be one more video because I'll be missing 2 days. I'm going to hold you accountable to this. Despite there being a sub, despite me not being there personally, this is good enough. This is plenty good enough. This is an experience that not a lot of people get to have when their teachers are gone, okay? We're not falling behind. We're staying on track. If there's something that you didn't get, go to tutoring. There's after school tutoring in the libraries on Mondays, Wednesdays, and Thursdays. If you did not follow something here, then go to tutoring. If you didn't follow something here, talk to a friend. If you didn't follow something here, watch the video again. If you didn't follow something here, Miss Sherwood has her own notes that she scanned in on Canvas. You can go look at the way she did something. Maybe she did it a little bit differently than I. Okay? But we're not falling behind. We're not going to sit here and... I know I'm ending on like a sour note, but I need you to stay on top of it. Okay? I need you to stay on top of it. We're going to keep moving forward. Okay? Hopefully you appreciated the video. Like I said, the streams are just like this, right? Except you get to ask a question. Right? Live, anonymous. You get to post a meme. You get to do some emotes. You get to do whatever you want, right? So, yeah, there will be a stream at the end of this unit like usual, and we will review. But yeah, thank you for watching. I went slightly over my 55-minute mark, but that's okay. Have a good day. What day is today? It's going to be Thursday. So there is tutoring today. All right. I'll see you.